Right. So I decided to record a video to go over a little bit more of the in-class exercise for regression. So this hopefully would help. So the idea of regression is basically you have some kind of input x, and you want to put that into a function, and you have some kind of output uh, that you predict. So if you have the data input x and the label, you have this and the label. The idea is that you want to find a function such that such that your prediction and the true label are as similar as possible, right? Ideally, you want your prediction to equal to the label. And in order to achieve this, what we do is we minimize the difference between them. So if you put a sample in here, the difference between them is the error, right? Now, if you can square them, which will still be the same thing, and then if you take the average error, so if you sum up all the error from 1 to n samples and you divide by n, so this right here is the average error. So your goal is to find a function f that essentially makes the average error as small as possible. Okay? The issue with this is that you don't know what the function is. So what we do is we make an assumption that the function looks like something. So in this particular example, we're going to assume that the function looks like a line, right? So the function looks like a line, w1. Notice how this is the equation of a line. So if the function looks like a line, but at this point, we don't know what W1, W2 is. When we don't know what W1, W2 is, we don't know what exactly, it could be any line, right? But once we find the best one, ideally, this will be the line that gives us the least amount of error, right? The least amount of average error. So if we define the function as this implies that if we put multiple points, x1, x2, x3, x4, we put all the points in, this is equal to wx1 plus w2, wx2 plus w2, x3. So this is what it means when you put each point in there. So this could be rewritten as x1 1, x2 1, x3 1, x4 1, w1 w2. So this is what we want to multiply. So what happened is if this right here is written this way, we can rename this as x1 x and 1 and w1 w2, right? So for every single sample, what's happening is we're multiplying w by this. And we're going to call this phi xi transpose w. So this is w, this is so when we so when for this function, instead of writing the function, we can write it this way, which implies that we're trying to minimize the average error I equals 1 to n phi of xi transpose w minus yi, right? Because this is how we define the function. Once we define a function, we just need to know what phi x1 is, phi x2, phi x3. And this is it. This right here is phi x1. This one is phi x2. So let's plug the numbers in. What is 1? So the numbers are 1, 2, 2, 3, right? So this means that it'll be w times the first one. So it'll be 1, 2, 2, 3, 1, 1, 1, 1, w. Now that you know phi 1 to 4, this is just a vector. So you know the vectors. All you have to do is minimize this. To minimize this, we need to find the derivative of this to perform gradient descent. The derivative of this is, let's see, take the derivative is 2n summation I equals 1 to n phi xi transpose w minus yi. So you got to take the chain rule, take the derivative of what's inside with respect to w, then that's this. So this right here is the derivative. dl dw. So now, to perform gradient descent, all you need is follow w next is equal to w now minus eta dl dw at w now. Okay, so this is the math. Now we need to do the programming. So what I first do is I create this matrix here, which I'm going to call it phi. Okay. So the matrix phi is right here, and notice this is exactly the same. Okay, so I created the matrix phi. Well, after phi, I want to know how many samples there are, because when we're looping through, because there are 4 samples, so we need to know that n is equal to 4 here. And after that, I want all the labels. So y is a vector of all the labels. Now, we initialize w, so because you need to set it to something. When you're running gradient descent, you have to set it to something so you can start the walking. So you can set it anything. So I set it to 0 and 1. Okay, so I now I have gradient descent started. The function we're trying to minimize is this here. So let's define the function. And what I do is I essentially multiply this. This is right here, minus yi square. And all I do is I just add every single sample. So zip allows you to loop through the rows of each, right? So as you loop through, you got phi 1, phi 2, phi 3, phi 4. Similarly, y1, y2. So for phi 1, y1, right? Phi 1, y1. For those, then basically I have this, and I'm just adding them together. Now, for those of you that's not familiar with this, the notation is equal to f0 plus this thing here. Okay. So in the end, then I divide by 1 over n. So once I add everything together, I divide by 1 over n. Now, you want to make sure you export when you return a value. Right now, this is returning like a number inside an array. So if you don't want a number inside array, you put item. And instead of that, this will equal to just 4. Notice no more brackets here. So that's what the item is for. Okay, so this idea here is basically all I did is define the function. Next, remember that the derivative is calculated this way. So let's calculate the derivative given w, right? So, well, I start off by just defining a derivative of zeros. So zeros, because I'm going to keep adding them together. So what I do is notice how this is w transpose dot phi minus yi, right? So this right here is exactly the same. And then I multiply by phi. So basically, I take this just like this, and I loop through and just sum it all together. After I sum it together, I multiply by 2n. Okay, so that's what happened here. So now we have the function, we also have the derivative. We just need to run the gradient descent. So I loop through, I pick 400, but you can pick more or less. When I loop through, every single time I simply calculate the gradient. I calculate the derivative at this point, and then I update w, and I take every single time I take a new step and a new step towards the best w possible. And every single time I calculate for every single gradient descent step, I plug the w into the function. So this basically tells us that given the new w, is our function going down? And so given every single step, our function should be going down and down and down. So this allows us to visually see it. Okay, so after I run this, then I print out what the best w is, which is roughly 0.5, 0.5. And then I write the predictions. So these are the predictions. So our y value was one. What was it? One, nope, 1122. So we are trying to predict this 1122. So this didn't do that good of a job, but well, you kind of can't do a good job better than that. This did a good job. This did a good job. Okay. So after this, we now know the best w, because the function is equal to w1x plus w2. So if you know w, which is w1, w2, we can just plug it in. So the function is basically the first w and then the second w right here. So now we have the function. Yeah. So this allows us to plot it out. Okay. So this code here tells you that this subplot basically says it's 1, 2. So you have 1 by 2. So you're going to put images that looks like this. And then this 1 tells you is the first one. So I'm going to draw essentially the points. So these are the data points I have. And this is the prediction. Notice how this prediction basically it's impossible for you to draw a straight line to connect everything. So this is the straight line that gives you the least amount of error. Hmm? And then I also plot out all the functions. So as we run gradient descent, every single step, you can see that it's incrementally getting smaller, implying that the average error of our prediction is getting smaller and smaller as well. So this is what this code is doing. The goal is first you need to understand the objective, and then you need to understand gradient descent, and then by stepping through this code, hopefully you can see how we end up drawing a line that give us the least amount of error, right? So that's it. I hope this is helpful.